Welcome again, everybody. My name is Jeroen Bunk. I'm from Blue Terra Energy Experts. It's one of the partners of the Comsos project. And you will attend today the webinar about Sfc technology. We're gonna explain all about it this afternoon. You have a lot of opportunities to ask questions. You can ask them in the chat. They will be answered right after the presentations and in the Q&A at the end with the manufacturers. Program of today is as follows. There will be first of all a presentation from my side which explains the project Comsos, and then I will dive into SOFC technology and its role in the sustainable energy system. After that, Marta from Politecnico di Torino will tell something about market analysis and business cases. And after that, the manufacturers get to say something regarding their experience with SOFC and their products. And in the end, there will be a Q&A and discussion. So, but first of all, my presentation. So, I will dive into the project's SOFC technology and its role in the energy system. So first of all, about Comsos. Comsos stands for commercial scale SOFC systems. And SOFC is a type of fuel cell, which I will tell you more about in a minute. The period of the project is from 2018 up to 2022. So we started already in 2018, and next year we hope to finish the project. It's an EU-funded project, and we aim to validate and demonstrate fuel cell in the power range of 10 to 60 kilowatts, and it's about combined heat and power solutions. So in the power range of 10 to 60 kilowatt, which is called mini FC CHP products. The target is to implement 25 SOFC technology-based power units around the world. Besides the installations of these power units, the activities also include a market analysis and business case analysis to show the potential of the different markets and optimal scenarios for the installation. We do also performance analysis and emission analysis to show the environmental benefits of a fuel cell-based cogeneration units. And last but not least, we try to create awareness, and we try to disseminate our results and show the public the benefits of fuel cell systems. So the Comsos partners, it's a EU-wide consortium which contains 3 manufacturers, which is Convion from Finland. Thomas Kala will present something about Convion later on. Solid Power, which is an Italian Swiss company, which also has a presentation by Stefano Medina. and Sunfire, which is the last manufacturer. Then we have Research Institute VTT, which is the coordinator of the project and does the emission analysis. And Politecnico di Torino and Blue Terra are focusing on the business cases and market analysis mostly. Then about the systems. As I said, there will be 25 systems installed within this project, this Comsos project. We have now one system up and running, and for all the others, the sites are already chosen, and all preparations are made to install the systems. But since it's worldwide, we have also some problems regarding like the whole COVID situation, of course. But we are expected that all systems will be installed soon. Okay, that was it about the project, and we can dive into the technology. So a fuel cell includes an anode, a cathode, and an electrolyte. And the basic principles are the same as batteries, and with the difference that fuel cells are continuously fueled. Within the fuel cell, a chemical reaction takes place, and electrolyte starts running from the anode to the cathode, which leads to electricity production. At the same time, heat can be recovered from the system, which makes it a CHP solution. There are different types of fuel cells, which can be which are characterized by their operation temperature and the electrolyte type. Sfc is a high temperature fuel cell, so it's operating between 700 and 900 degrees Celsius. And the electrolyte is solid ceramic. So then what are the benefits of the SUFC? So it has a high electrical efficiency compared to conventional technologies, as well as to other fuel cell technologies. And there's also a high overall efficiency in case of heat utilization. This heat is high temperature heat, which can be used to warm old buildings or something like that. So it can be used to heat with temperatures of around 70 to 90 degrees. The materials are non-toxic, non-critical, and non-expensive. And using a fuel cell leads to a minimization of local emissions with no particles, no NOx, and no CO. One of the big advantages of using SUFC is that it can run on natural gas as well as H2, syngas, biogas, propane. So it's multi-fuel flexible, which is a great advantage in like a changing energy system. The process is in principle also reversible. So with electricity, you're able to produce hydrogen. So in this electrolysis mode, can be done with the same cells and stacks, but the system needs some more adaptations. Okay, that about the cells. These cells can be stacked together, and then you create a stack unit And these stack units have a standardized design and can be then used within an SUFC system, which has all other components that support the working of the stack units itself. So the current fields of applications of SUFC. So because of its characteristics, with the high efficiency and the high temperature operation, SUFC is mostly interesting for stationary CHP systems compared to PEM, which is PEM fuel cells, which is another type, which also is used in the mobilization sector, for example. SUFC has already like a broad application in micro CHP solutions, which are residential systems to warm and electrify homes. And already more than 10,000 systems are installed in Europe, and more than 100,000 systems are installed in Japan, which had a very interesting subsidy scheme. SUFC is also used for off-grid power generation, and that's because of the low maintenance cost and the little maintenance is needed for such systems. There's also large-scale solutions, and those are in the range of 1 megawatt. They are often used for data centers because of the high reliability of SOFC fuel cells. So, as said, Comsos is focused on mini CHP, and that's in the range of 50 to approximately 100 kilowatts electric. And this market now starts to grow. Now, what is this market? The market for micro CHP are buildings or sites that need reliable electricity and heat production, and wants to lower their carbon emissions. The potential customers would be hospitals, hotels, restaurants, or other small or medium enterprises. Marta from Colito will tell you more about it. I will focus my presentation on the role of in the energy system. What role can micro CHPs of mini CHPs play in the energy system now and in the future? Because the energy system is in transition. There's a need for an energy system that is resilient, secure, that's efficient, but which remains affordable for everyone, and which is clean, of course, doesn't emit any CO2. And it turns out that this requires a mix of energy solutions. Yeah, and we believe that CHP plays a crucial role in this mix. What you see is that you get with local energy production by wind and solar. There's a development of energy hubs and smart grids, which requires system integration. And CHP has a crucial role in between electricity demand, heat, and gas demand, and it connects all these systems. Moreover, since it's a dispatchable source of energy, it can mitigate the expected imbalances in demand and supply, and there it complements in that sense electrification, demands and response, energy storage, and power-to-X solutions. But since it has this connecting role in this system, it's a crucial element. Well, to come to that, to such an energy system, such decentralized energy system, the energy transition faces some challenges, which a mini CHP can really be helpful in. So first of all, there's a struggle with the integration of sustainable fuels, and the fuel flexibility that solid oxide fuel cells offer is a huge advantage in an energy system in transition, and actually could resolve the chicken and egg problem regarding the implementation of hydrogen, because you can actually have blended fuel. Well, we all heard about the rising energy prices. I believe that today and yesterday the price again rose about 20% of gas, and that requires a high efficiency of the energy conversion systems. And Sfc can offer these high efficiencies. This will remain important in the future if you have renewable gases, which tend to have higher costs than like the conventional fossil fuels. Therefore, like the high efficiency of SOFC is a really important element. Another thing that's is happening today is that there are a lot of countries that are struggling with the NOx restrictions that there are, and the problems regarding air quality. In the Netherlands, we had like a nitrogen crisis, it's called, but also in Germany and Portugal, the EU already asked to have to enforce the regulations stricter. In Belgium, one of the large energy plants that needed to replace the nuclear power plants didn't get a license to operate because of the NOx regulations. So this is going to be a major factor in the coming years. Since SOFC has hardly any NOx emissions, it can be an alternative for NOx emitting energy technologies such as natural gas, CHP, or biomass CHP. Last but not least, we have the infrastructural issues. Power grid constraints increase due to the implementation of renewable energy sources and electrifications. And a study showed that by implementing fuel cell micro CHP, more than 2,000 euros for every kilowatt of installed capacity can be reduced by 2050. So, in conclusion, Sfc offers decentralized and dispatchable generation of heat and electricity. And it improves efficiency and decarbonizes and firstly eliminates local air pollution. And at the same time, it takes care of the integration of electricity, gas, and heat systems. So to conclude, it's a crucial factor in the seamless transition from the current fossil energy economy into a sustainable energy economy. So this was from a system perspective. Marta will tell you now more about the business cases for companies itself.
Thanks, Jaron. I will now share my screen. Okay. While speaking, I will just switch off the camera, not to have internet issues. Okay. So I will now tell you something more about the market analysis and business case analysis that we developed in Politecnico di Torino, together also with Jaron from Bluterra. This analysis has already been partially published, but we are still working on this topic. I will try to give an overview of what we have done, and later on, if you have a question on, or if you want to see more numbers, we have all the documents available. I think that the context was already well explained by Jaron, so I won't spend too much time on this. Our idea is to study the benefits, both technical and economical, of installing an SFC in the commercial sector. When talking about commercial sector, we talk about a lot of buildings, non-residential buildings. In Europe, there are specific projects related to residential building, while Comsos was aimed at looking at this specific market. Here you can see some example of non-residential buildings. So the hotel, the supermarkets, all the sports centers, schools, restaurants, hospital, and so on. I will show you some example among these ones to explain why these kind of buildings are interesting for the SFC application. In all our analysis, we consider to install in the SFC scenario this cogeneration unit producing electricity and heat fed by natural gas. Of course, as already said, the system can be also fed by a mixture of nitrogen and hydrogen, or by pure hydrogen. So there are also some other upgrades that can be considered. When a building decides to install a solid oxide fuel cell, usually a gas boiler is already available within the building, and so it is anyway used to compensate the thermal request. And the grid could also be used in case the demand is, let's say, is flexible. We will see some, if there are some variation compared to the SFC production, the grid can provide some just residual electrical power. And we compare this SFC scenario with the reference one that usually, but we will see there are also other options, is a simplified system where all the electricity is taken from the grid and all the heat is taken from the natural gas grid through the use of a gas boiler. Concerning SFC, just looking at some technical details, SFC are flexible systems, so we can operate them varying also the nominal power, usually in the range of 50% to full power. The electrical efficiency is very stable and very high, so there are no problem in modulating the power. If we go below 50%, it's feasible in some of the product on the market, but let's say it's more difficult from the point of view of the balance of plant, not because of the stacks. On the contrary, shutdown and startup should be minimized because we are talking about a high temperature system. even if, as I said, it is possible to operate the system flexibly, and it's also interesting in some specific application, given the still quite, let's say, high cost of the technology, the best solution up to date is to use the SFC working, let's say, 24/7 continuously all the year. So the best solution is to maximize the capacity factor of the system, because these, of course, increase the operational savings and results in a better economical scenario. In these graphs here on the bottom, you can see an example of a demand profile, hourly demand profile. And one option that usually is the best one is to size the SFC on the base load, so that all the energy produced by the cogeneration unit is self-consumed by the system. And this, let's say, requirement of a base load is something that is typical of the commercial sector. And here there are some examples. If we look at the supermarket and in general to the, let's say, commercial centers, but where there are supermarkets inside, we can find in this graph on the right, you can see the base load. We can always find the base load. In the supermarkets, the base load is dominated by the use of the refrigeration system. So all the both in fridge and frozen foods need to be kept, of course, at low temperature during 24/7 all the year. And so this is a very good base load for our product. It is also important to say that these kind of systems usually we have analyzed all the market, and here there are some numbers, usually also have a size which is comparable with the product available in the SFC market in Europe nowadays. So tens to maximum 100 of kilowatt, which is good for our producers. The same base load, electrical base load, can be found also in the hotels. Again, we have done a deep market analysis on the hotels. And here, again, you can see the electrical demand on an hourly basis for a typical day in different time of the year. But you see that even if the electrical demand is changing during the year, the base load is always guaranteed. And in this case, it's 100 kilowatt because it's on an hourly basis. So again, the hotel sector is another interesting market because it shows this base load for what concerning the electrical. Finally, another interesting application is the one of the hospitals. Hospitals usually have higher demand in terms of size, but one interesting, let's say, features of the hospital is that they have this electrical base load for all the technical equipment, but they also have a continuous need for natural gas, so for heating and domestic hot water throughout all the year. So we will see heat is an added value of the cogeneration unit, is less monetary interesting than electricity, but still is very good when we found users that need it. For example, also in the hotels, very high-level hotels usually have a sauna or swimming pool, and so also in the hotels there is the possibility to use the heat throughout all the year. And this is just a figure showing that in different European countries, the commercial building sector is quite important. It's the green bar over the total building stock. And so this is quite interesting. Our analysis is focused on commercial building, but also on small offices and small industries, so small business sites. What we have done, our business analysis and also the market ones are all based on data that we have, let's say, retrieved from the manufacturers. We have asked confidential data to the 3 SFC producer, and we have produced a generic SFC module in the range, as said, up to 60 kilowatt, which can be representative of the European market. Then, of course, every producer has its own features, you will see later, but for the analysis, we have considered a general SFC system. Our models includes information about the degradation and the lifetime of the system, both at current and target values. And of course, there are all the details on the energy prices. As said before, energy prices are strongly influencing the economics of this installation, and also incentive scheme and taxes. We will now look, let's say, go through the value drivers part. Concerning the energy prices, these are, let's say, data up to this year. What is very interesting, I will show you some numbers, is the spark spread. So the relative difference between the electrical and natural gas prices. In Europe, we have some countries, like also Italy or Germany, for example, where the electricity price is very high. And the gas price, this of course is not updated in the last months, but is relatively low compared to electricity. In these scenarios, it's very interesting, the installation of cogeneration unit, because the production of electricity starting from natural gas, it's convenient. Talking about the value drivers, of course, the main value of an SFC installation is the electrical production. SFC shows a very high electrical efficiency, up to 60% net electrical efficiency from natural gas to AC power, so including all the auxiliaries. And this is, of course, this accounts for a 30 kilowatt system from 50 to 100% of the value of the SFC, which in monetary terms is also the highest one you will see. But even considering non-technical and non-economical value drivers, the electricity one is always the main, let's say, the main product of our system. Then we have heat. As said, heat has less, usually, depending on the application, has less monetary value. You see for the same 30 kilowatt system, its savings are lower compared to electricity ones, and they can account up to 10%. And this is mainly due to the type of application. So if there is a strong seasonality in heat, it's difficult to recover heat during summer. You can have other equipment, of course, to produce cold power from heat, but this would increase the investment. So it's interesting in this case to look for application who also needs heat. And as I told you, in the commercial sector, there are applications which requires heat. And also, of course, the lower we are able to go in temperature with the heat source, the better it is for the recovery. Other important drivers could be the reliability. There are countries in the EU area or in the US, specific geographical location where the grid is not reliable. And so industries or centers or supermarkets can have problems of interruption. In this case, they need usually to go for a backup power. But, and this is, of course, another cost we see in numbers in the next slide. When using an SFC, there is the possibility of working in island mode. The SFC is able to work if natural gas is available, even without the electrical grid, and to supply the load. And so it can guarantee some secure loads. The reliability of the SFC is something very interesting, especially for application which needs 24/7 continuous power without interruption. And of course, there is all the environmental part, which is not was not mentioned until now, but it's also very important. When going from a conventional system to an SFC, the reduction in terms of CO2, but especially in pollutants, for example, NOx is very huge, because NOx are of course emitted by a traditional boiler, and they are also virtually emitted by the grid, by the thermal plants producing power in the grid. While our SFC system, let's say all our measurement that we have done in the Comsos project, there are already data from the installation. You can see in the Comsos website. They are all below the detection limit of the instrument. So this data that you see here in this graph 48 is not, this is a yearly evaluation for a typical hospital, for example. This is not a value that we have measured, but it's the detection limit of the instrument. So NOx emission could be also lower than this. We should say lower than 48. And for another example of value driver is related to the world of data centers. Data centers are interesting market for fuel cell because again of the reliability of the power supply. Thanks to the use of a fuel cell, the data center can increase what they call the tire level, which is the let's say the percentage of guarantees of uptime of the power to the data center. And this, in monetary terms, for data center is very important. So we will see later in numbers, but these 6,000 to 12,000 per year of let's say savings can generate a reduction in the payback time of the investment of up to 2 years. So summarizing, these are the value drivers that have been analyzed. I have only discussed some of them, just the more, say, important ones. So of course, the electricity, the heat, but also the avoiding of purchasing of the backup power because of the possibility of the SFC to guarantee continuous supply, or also the reduction in the stress to the grid in some areas. So even if the scenarios is changing a lot, market to market and application to application, the typical customer is a customer with a base load profile in terms of electricity and the low fuel price, which usually low fuel price means that the site has a high additional fuel demand. So if the site is consuming a lot of course, fuel, then the price will be lower. And the need for backup power, and so a high value of lost load is another stronger incentive for the installation. And here there are some numbers. I will maybe go to the target ones. These are data on the payback time in the top countries in Europe for the 30 kilowatt system in different commercial sectors. And so for each of them, we have considered different value drivers and different price of electricity in different sizes. And you see that at target cost for the SFC, the payback time is on average around 5 years or even lower, without considering the backup power saving. So the scenario is very good. At the current cost, the situation is, of course, a little bit more critical without considering subsidies. But we have seen that with the use of already existing financial schemes, and this is where I will go now, there is the possibility of reaching, let's say, acceptable payback time even in the current scenario. I will just go quickly to the end. There are also other business models for larger systems. So if we go up on plants larger than 100 kilowatt, of course, power purchase agreements or rental contract could also be very interesting, and this is something that we have analyzed. We have also analyzed all the big discussion on the grid balancing. So the inclusion of a fuel cell in a virtual power plant for making grid services. This is, of course, not, let's say, so much interesting for a commercial building alone, because usually the consumption is below the ranges for the grid balance for entering the market. But it could be interesting for larger applications. So it's for future projection, let's say in the future with larger SFC systems could be an interesting opportunity, because FCC can modulate quite fast their power, and so they can do this kind of services. In terms of financial scheme, we have analyzed the current available financial schemes in Europe. Many of them are in the form of feed-in tariffs. These are, let's say, interesting, but they don't solve the issue of the quite high investment cost. The best solution are the grants or the investment on the subsidies. subsidies on the investment. These have the major impact because they can reduce at the beginning the investment cost, and then of course during the lifetime the SFC has a very low maintenance, and so the operational savings are occurring anyway, even at current cost. And the need for specific subsidies is something which is very important. In this graph, you can see the increase in blue of the installation of the installed fuel cell unit, both PIM and SFC in Japan, in the framework of the NFRM project in residential buildings. And together with the increase of the units installed, the price fell down of 3 times at least. So there are, let's say, a real case study in the world that shows how even continuous, even small but continuous incentives on the technology can really help in reducing the investment cost. This is a final overview. Maybe we can also leave you the slides later so that you can have a look. But for all the building types, we have defined a typical base load. How much base load can we cover, and how is the heat utilization and the value of lost load, and so the capacity fit, and so which are the best markets for installing an SFC. So to conclude, and sorry for being a little bit late, we have a product here which is an SFC which has very high technical and environmental, because the environmental part I think is also very important, let's say, advantages. And also what is very important is that they are very flexible in terms of fuel and in terms of operation. The profitability currently depends on the market, on the energy prices, on the regulation, but there are some niche markets on some specific applications, like some of the commercial building that we have seen, in which also nowadays with the available incentive, for example, in Germany or in Italy with the energy incentives for the renovation of the buildings, the SFC could be a very interesting product. So this is our main funding. All the documents that we have produced on this market and business analysis are available on our website, so you can download the complete description of what I show you quite quickly now. And we have also a publication on this, so all the material produced is public. And thank you for this, and I am available for questions. Maybe I think we should do it after the presentation in order to not to lose time during the agenda. Thank you.
Thank you, Marta. And it's now time for Stefano Modena from Solid Power.
Yeah, okay, thank you very much. And thank you for the opportunity to be here and to present a little bit some activities that we are doing as a company. I'm okay, sharing the screen. Okay, perfect. No, since it doesn't work, that's something that. Okay, now since, oops. Okay, sorry. Yeah, just a few words about myself. Just to present myself, I am Stefano Modena, working in Italy, in the Italian branch of the company, in the headquarters that is located in Trentino region, in the north of Italy. I joined the company in 2007 when it was founded. I am now project manager, so I have this role in the company. Just a few words about the company. The company was founded in 2007 with Sfc Power name. After that, company acquired HT Ceramics, that was a spin-off of EPFL in Lausanne. We built the first pilot production plant in Italy, in the Trentino region in 2008. And we acquired Ceramics Fuel Cell Germany in 2015, acquiring also some assets of the previous Ceramics Fuel Cell, including the BlueGen technology, the BlueGen product, BG0, that we launched again on the market in 2016, together with other products available in the following year, like the BlueGen BG15 in 2019, and in 2022 next year, what is called BlueGen BG60. This is an overview about the status of the company. Company is also producing stack, the stack that is used and integrated into our systems, into the micro cogenerators, and the stack is produced in our plant, in the stack production plant. You can see here a picture that is also located in the Trentino region. I have one slide showing some more pictures about this plant. What about locations? So we are located in 4 different countries and regions. As said before, in Switzerland, in Yverdon, in Italy, in Melbourne, in Australia, where we have R&D technical departments mainly, and the production and assembly is located in Italy and in Germany, where in Germany we are assembling the system, so we are integrating all the components into the final systems, and in Italy we are producing mainly the stack. In the new facility plant, as I said before, we have built up this new facility that is the largest one in Europe for the solid oxide fuel cell manufacturing. The capacity is 25 megawatt per year, expandable up to 50 megawatt with minor adjustment in the building. But as it is now, we can reach a 25 megawatt per year. That makes the facility the largest one, at least in Europe, for solid oxide fuel cell technology. In this facility, we are manufacturing the stack, starting from the power. We're producing the cell, the repeating element, piling up together in the stack, and the stack is integrated into the final system. As you probably already know, the technology, solid oxide fuel cell technology, can be used in several applications. Can be used as, let's say, CHP, as a combined power and heat device, so using gas and water to produce power and heat. But the same technology can be used also in the electrolyzer mode to produce gas, so starting from power, in this case producing gas, hydrogen, starting from power and water or vapor, or a syngas mixed by hydrogen and CO. Starting from water and CO2. But the technology can be also used in the power-to-power assembling mode, particularly for long-term energy storage. Our technology can be used, and our stack can be used in all these applications, and we are experienced in all these applications, even if today I'm talking more about the micro CHP and not the system that we are going to deploy in Comsos, but much more about the unit that is already commercialized worldwide, in principle, and particularly in Europe. But we have assembled and we have installed it also in other parts of the world. And here I'm talking more about the BG0 and BG15 that are our current products, particularly the BG15 that was put on the market in 2019. It is based on 1.5 kilowatt power output with a 57% of electrical efficiency. We have these numbers, so we have more than 2,500 units installed, BG0 and BG15 mainly. We have installed also some, as you can see here in this picture, what is called Engine 2500. The engine was the product, the system that was developed particularly within NFIL program. We installed heat more in Italy, partially also in Germany. Now, as I said before, our commercial products are the BlueGen, BG0, BG15, and our future product will be the BG60. Up to now, we installed more than 2,500 units in 12 countries, achieving more than 42 million hours of operation. That's an important asset for us, an important value for the company. I guess that 42 million of our operation means a lot of experience also in the OPEX, in the operations, and in the maintenance of the units that make Solid Power really a company with a strong experience on this kind of activities. Our units, our products saved 53 gigawatts, produce 53 gigawatt hours, saving more than 11,000 tons of CO2. Something about performance, the stack lifetime is 7 years, with a mean time between failure currently set to 5 years. So the mean time between failure is more or less 5 years, but with a stack lifetime up to 7 years, with a reduction of the efficiency in the range of 1.5% per year. These are the main figures, the main pictures coming from the fleet, more than 2,500 units, as I said before, of microcogenerators. Why microcogenerators? Something has been already said by Marta particularly, but microcogenerator because we can use methane, the fuel, particularly methane, but not only. The system can work with several fuels, currently methane, biomethane, hydrogen, a mix of hydrogen and methane in future, in order to produce power and heat with electrical efficiency up to 57% and 31% thermal power, thermal efficiency. So it means a cogeneration efficiency in the range of 90%. And the advantages of the microcogenerators are mainly because integrating the use in the existing gas network in the complementary way is possible to produce electricity and expanding the electricity grid. In this sense, the investment on the grid can be kept as low as possible. Cogeneration plants can help cover the base load even when renewable energy is not available on site and relieve the electricity grids. Local electricity generation and the use of the resulting thermal energy, a low efficiency, as said before, up to 90%. And the use of the fuel cell makes this process extremely efficient, 57% of electrical efficiency at this power size is something that is not possible with other technologies. What is our product position? Let's say our product portfolio. As I said before, we have the BG15, the 1.5 kilowatt output, and we have the BlueGen BG60. We are going to deploy this unit in 2022, also within Comsos. And the BG15 can be used and address several applications, several markets, particularly homes, multifamily homes, in the cascading configuration, also hotels or restaurant, larger application, hotels or restaurant, hospitals, and so on, will be covered more by BlueGen BG60 and the cascading BlueGen BG60. So the commercial application that Marta showed just a few minutes ago are much more covered by these systems in our view by BG60 than BG15. What the market is asking, we realized, is also a strong maintenance contract. That's also what we are trying to offer. With a monitoring system, monitoring platform necessary for guaranteeing a good high-level quality for the maintenance. The fuel cell module is also part of this maintenance contract. We are going to replace the stack and the fuel cell module if it failed when it fails. including also some other consumable materials like filter, water filter, air filter, and so on. That's something that we realize that the market is asking, and we are trying to offer them, not only, let's say, with the product, but also with this maintenance offer. A couple of business cases, just to conclude. This is a business case. Based on a real building. This is the blue line is the power demand of the building, and the green line is the power output of the BlueGen in a continuous and steady state operation at 1.5 kilowatt power output. Here on the right part, you can see the self-consumption of the building. So it means the percentage of the energy that is used by the building, produced by our system, by the BlueGen. In this case, the 1.5, the BG15. And the autarky, so the independence from the grid, 91% means that the building, the end user, is capable to be independent by the grid, from the grid by 91%. Only 9% of the energy is taken from the grid, basically. This is the case of the BlueGen BG15, 1.5 power output in a steady state. But the system can also modulate, and this is another feature, modulating between 30% and 100% of the power. We can follow much more the profile of the end user, increasing the self-consumptions, basically, up to 52%. So just giving this feature, that is also another feature that is asking by the market, in order to be able to profile the load of the unit, we can follow much better the load profile, and we can increase the self-consumption. The other case that I would like to propose you is the BG15 with a battery, with electricity storage. In this case, we can see here, again, the power demand of the building, the charging status of the battery, and the green line is the power output of the BlueGen. So keeping the power output constant in a steady state, according to what is the profile, the load profile of the building, the battery will decrease, will discharge, basically, and will charge again when the power goes down. So the battery works as a buffer, basically, and this helps to increase dramatically and significantly the self-consumption of the building up to 70%, keeping the autarky at 90%. This is the case of the household where we installed the BG15. The other case is the BG15 plus the battery and plus the heat pump. We have also several cases in this configuration, including the heat pump and the battery. In this case, we can increase again the self-consumption, and particularly also the autarky, up to 99%. Of course, the electricity used by heat pump in this case is provided by the power output of the BlueGen itself. So the combination of different technologies like our system, microcogenerator, with others. Okay, the other business case, the last one, is the case with the electrical car. So the BlueGen, the storage, the heat pump, and the electrical car. So showing how, let's say, the profile and how the produce of the power from the BlueGen can work together with a very good value of self-consumption and autarky again. The combination of different systems, what we are calling here system integration, is providing several advantages. This is our experience, our real experience of the market, because it helped to increase the power generation and the efficiency of the power generation, mainly, to grow the decentralization of the power generation and the sustainable decentralized power generation by innovative combination and the plant optimization. So all these advantages together gives a very, very good, let's say, experience to the customers, together with the advantages, the main advantages of the cell-to-cell fuel cell. I'm not going to repeat. Many of them are already said in my presentation before and by Marta, so I don't want to repeat them. But the electrical efficiency, the quiet operation, the CO2 reduction are really important driver for this kind of technology. So I'm going to finish, and I would like to thank you for the attention.
Thank you, Stefano. Very interesting to hear the perspective of the manufacturer. Thomas, can you start your presentation? I can't hear you yet.
How about now?
Perfect.
Very good. Okay, thank you, Jörn. Thank you for this opportunity and for the presentations that sort of laid ground to what I'm going to say next. I will share my screen. Please let me know if you see it correctly. My name is Tuomas Hakala. I'm a co-founder of Convion. Convion, do you see the screen?
Yes, yes.
No,
we can
very
see.
good.
Yeah.
Very good. Okay. Convion is a company specializing in fuel cell systems, or solid oxide cell systems to be more precise. The company was established in 2012 already by a team. I was one of the team, a team with a history in fuel cell systems related R&D within Wärtsilä Corporation. Throughout our history, we've focused on system technology, so that means we don't develop cells or cell stacks. Instead, we have cooperated with all the leading manufacturers of cell technology, because we see that the competencies and perspective required for system development and cell stack development are quite different, and therefore we prefer to work with those who do the cell technology best. We have a considerable intellectual property portfolio relating to system technologies that are applicable to both fuel cell, which is power generation systems, as well as electrolysis, high temperature electrolysis systems. Even on a product level, you see that the images here, there are plenty of similarities. Obviously, the use case differs, but we'll be able to utilize the know-how of integration and process and control, and some of the part of the supply chain in both of the systems. Today, I talk about fuel cell cogeneration systems, because this is the topic of the Comsos project. Worked on systems that are somewhat bigger, often referred to as mini CHP instead of micro CHP. We see that in commercial and industrial applications, there's plenty of unmet demand for local generation, and a suitable building block for this kind of applications is in at least tens of kilowatt. The hand is a modular technology, and it doesn't make sense to make the building block, the basic repeatable unit, very large. You can build several hundreds or up to a megawatt scale of systems out of small or smallish individual and independently operable modules. We have years of experience of fuel cell and fuel cell CHP product development and deployments in different countries. Also currently ongoing demonstrations. The high temperature electrolysis is newer development within our company, and we will demonstrate the first unit next year in an application where e-fuels are produced together with partners. The basic product, which I've referred to, is a 60 kilowatt a module with 60 kilowatt electric net output. It has a design 60% net efficiency and capability to offer approximately 24 kilowatts of heat as a byproduct. It's an option. This system can be configured to use either natural gas or biomethane or digester quality biogas as a fuel. Also, we've explored the opportunities to use hydrogen, at least in a blend, and we can say that this unit can be run with a blend of hydrogen up to some tens of percentage points of hydrogen in a blend with minimal effect on the performance or the efficiency. But it's not optimized for pure hydrogen, but that can also be done. It's just not within the fuel envelope of this product. The guiding principles of our product design have always been simplicity, flexibility and performance, meaning that in order to meet the market demands for reliability and ease of use and ease of deployment, together with meeting CapEx and OpEx targets, we've had to do a lot of simplification of the core system and its interfaces. And we're quite satisfied with the results. This is an all-in-one little power generator that only needs to be connected to a gas grid and power grid. It doesn't require auxiliary systems, and it is up in operation within hours from bringing it to the site. The design can be adapted to different stacks. Today, the stacks within the systems that are in operation are from Elcogen, but we've kept the flexibility to use stacks from different manufacturers. These systems are designed for outdoor installation. They don't require any water at any moment, and we live in Finland, and the conditions sometimes are such that that is a clear benefit of not having to have liquid water anywhere. And like was already explained in the earlier presentations, since we don't combust anything, the emissions beyond just CO2 are basically zero, the emissions of NOx or SOx or particulates. We've all grown used to the idea that power generation is something that takes place in big power plants, and it preferably out of sight, and that the sort of economy of scale always outweighs the trade-offs or vulnerabilities related to distance. But this is a sort of worldview that is due for a quick update. Recent trends, all of the recent trends in energy prove that an old sort of out of date idea, because solar power, battery storage and fuel cells are all modular technologies, and scale is not a factor in their technical performance. Therefore, aided with digitalization of assets, power generation can be co-located with consumption. And that not only helps us avoiding reinforcement investments in grid and transmission and distribution grid, but it also improves quality of service and helps us avoiding losses of transmission and distribution. We see that in commercial and industrial applications, there are locations where co-located fuel cell systems in sub-megawatt scale can have not only immediate OPEX savings, but also indirect savings in avoiding other investments such as backup systems or grid reinforcements. There are also particular locations such as waste and water services where self-powering these critical infrastructure systems by locally available biogas is an attractive option that is mostly underutilized or unutilized with legacy technologies, but fuel cells change the game. Here's a view of some real-world examples, and the photo shows the conditions in Finland and why our systems are always put into ultimate test. This is an example of a utility hybrid microgrid by Lempäälän Energia, which is a energy utility, a regional energy utility here in Finland, and they built a new business district, completely new business district that was made a self-sufficient energy system as well. It has plenty of solar power generation. It has biogas gensets. It has multiple battery storage systems and fuel cell systems from Convion. The idea there, part of the concept, is that fuel cells are connected together with battery storage, and therefore the battery storage can offer the dynamic capability up to a megawatt scale, while 120 kilowatt of fuel cell capacity feed that in, making it like an infinite battery. And then heat in the setup can be recovered for low temperature local district heating network. It's an example that we see. It's an ambitious project, but we also see it as an example of where the future energy systems are going. There's not going to be one technology that sort of solves all the problems, but smart integration of multiple technologies and sources of energy help keeping the emissions low, improve the service quality, and avoid unnecessary or indirect investments into infrastructure. These are snapshots of those systems in operation, just highlighting that the high efficiency is proven. On the left-hand side, we have nominal operating point 60 kilowatt, over 60% net efficiency. The heat recovery system is not connected, so the numbers are indicative, but you see that the temperature of the exhaust gas above 200 degrees C, well suited for hot water production, not so much for steam production. In part load at 45 kilowatts operating point, the efficiency is actually higher than in the nominal point. That is net efficiency 64%. While fuel cells or high temperature fuel cells are not necessarily known for their highly dynamic performance, they still show very good part load capability in terms of efficiency. And in case of our systems, we have the normal setup is grid tied, which means that all the dynamic load can be taken from the grid, but if there was a power outage and our fuel cell system was the only generator or tasked to sort of generate the grid, it could use dissipative means to provide the millisecond level load following capability as well. Within Comsos project, we are going to deliver two systems. One again in a biogas application. Biogas, we have quite a bit of experience of biogas use in CHP fuel cell systems. We just closed a project called Demosofc in Italy, where wastewater treatment facility produced biogas, and that was fed to fuel cell systems. Now we're going to deliver one of our C60 fuel cell units to Estonia, to a company called Biomethane. Together we're going to explore growth opportunities in agricultural biogas segment in the Baltics. There the primary feedstock are solid agricultural residues or waste streams. The big opportunity here, the very idea of why biogas and fuel cells are a perfect fit, is that biogas intrinsically is a distributed resource, and it's usually very low energy density, and therefore transporting biomasses to places for conversion to energy doesn't make sense that much. But with legacy technologies such as turbines or piston engines, efficiency of small systems tends to be horrendously or prohibitively low, whereas for fuel cells, scale is not a factor, and we produce 1.5 to 2 times more of power from the same amount of gas as compared to those combustion technologies. It's a carbon neutral, local and dependable source of energy, and fits very well to be used alongside with other renewables that are time dependent. The other system that we're going to deliver within the Comsos project is again a CHP system configured to use natural gas or natural gas with hydrogen in a blend. It goes to a microgrid alongside with other technologies. It's a pilot, but the motive behind fuel cell, of course, is the very high efficiency. Electrical efficiency, because electricity is the most valuable form of energy, and because of the co-location of production and consumption, also heat can be used, making the total efficiency very high throughout the year. Microgrids are an interesting and quite rapidly growing segment, which provides a way to add new capacity without reinforcing the grid tremendously, and at the same time improve the quality of service, reliability, and then also facilitate the increasing of renewables in the mix. The partner, which at this point remains unnamed, is a major grid utility in China. Okay, I think I've used my time. This is all I wanted to say, and I'm open for questions regarding our product or business.
Thank you everyone. Can you hear me now?
Yes.
Okay, so thank you Jeroen, thank you Marta and Stefano and Thomas for the interesting presentation. We have a question from the chat, a question to Stefano Modena. It's a question about power-to-power system that was shown in the slide. And the question asks, in the power system, if the device, if the stack is used reversibly to produce hydrogen and electricity, and it's asking what is the switching time from a mode to the other one.
Yeah, I confirm that the stack can work both directions, so can work as let's say a reversible unit. We have proven it several times, so we have also experience about that. At the moment, we don't have, let's say, the final system that can work in this way. In future, maybe yes, but actually we don't have, let's say, a commercial application that we can put on the market. Nevertheless, let's say, just to mention it, we are working within another co-financed project, European project, that is the CH2P, where we are building up a system that is producing at the same time hydrogen, heat, and power. So in that case, it is not, let's say, a blue gen reversible, like probably you are asking for, but that's a system that produces at the same time the free values, so hydrogen, heat, but also power. Regarding the system in the reversible mode, the time for switching at the stack level is very, very fast. Can be done in less than 1 minute. Can be done very fast. At the system level is a little bit longer, but as I repeat, we don't have currently a system that works like that, so it is quite difficult for me to say something about time to give a value. But at the stack level, it can be done in a really fast way.
Thank you, Stefano. If I may, I can add an additional question about this. About the way in which hydrogen is supposed to be stored in this kind of system. If you can add some information for the power-to-power.
There are several ways, of course. We were involved in some projects where we used several kinds of tanks, pressurized tanks, or also metal-based systems. So there are several systems that can be used. We are working here, of course, not alone, but together with partners that are much more experienced than us on this topic, and can help in order to, let's say, to produce and to realize and to design the final system. But currently we're working in several directions. We don't have one single direction, but we are working together with partners using several technologies.
Thank you very much. We have still a couple of minutes. And there is a question. The question is from the chat. I think is addressed to Stefano again. It's asking, do you make use of electric preheating of the gases if you would operate the system in Surc mode?
No, electrical preheating of the gas, I would say no. We use eventually the heat itself to, let's say, to heat the gas, but not the electricity. So we don't have, let's say, in plan to use electricity in this case to preheat the gas.
Okay, thank you. We have another question from the chat for Thomas Akala. He's asking if the Convion system can work with different fuels other than methane and biogas, and for example, propane, DME, or other.
Yes, thank you for the question. This system, as it is designed, has a certain fuel envelope. Liquid fuels are out of question, and propane, of course, there is a little bit of propane in natural gas. We've explored possibility of using propane full time, but that's not something that we have validated or designed a system for. Of course, the solid oxide fuel cell technology itself can be adapted, and it's more of the system level design choices you have to make. Our team, we have built earlier on a couple of methanol fueled 20 kilowatt systems that one of them sailed the seas on board a car carrier ship, and at the time methanol was considered as a possible renewable future fuel for seafare, but we were maybe ahead of our times. That was already quite a long time ago. But so it's possible, but it's a matter of how you reform the fuel. As the system is designed today, we have identified natural gas, biomethane, or blend of hydrogen plus methane, or digester quality biogas as a sort of a sufficiently covering fuel envelope. But of course, if there is sufficient market for special fuels, then we'll be ready or able to consider.
Thank you very much. I think that we reached the time. It's 3:30. If there are other questions also from the chat or that come outside, you can find the contact that was shared in the slide. Yes, you can find the contacts of the project Comsos, the mail and of the speakers of today in the slide. So you will find the recording of the registration also, so it will be sent to the participant. That will be recorded and shared. And so I thank you all for participating to the webinar today, and I thank you in particular all the speakers, Jeroen, Marta, Stefano, and Thomas again. I leave the floor maybe to Marta if you want to say something to close for the Comsos project. And thank you all again, and all the public that was present to the webinar today.
Thank you to everyone for listening from my side. And as Domenico said, we will share with all the participants the material, and we will keep you informed about the Comsos project. On the project, there is also a survey on solid oxide fuel cell, which is aimed to understand the level of awareness of every people, let's say, in this sector on fuel cells. So if you have time and if you want, it would be nice to have also your opinion on this survey. And I don't know, Jeroen, if you want to close since you have opened.
Yes, I think everything is said. Thank you, everyone, and hopefully see you next time. Bye.
Bye-bye.
Thank you. Goodbye.
Thank you. Bye.
Goodbye.